Now that we've talked a little bit about quantum numbers, we can talk about why they matter. And so we're going to turn to what's called the Pauli exclusion principle. And I'm sure for folks who are coming out of the chemistry world, this is probably old hat to you all. But we'll go through and talk about the way electrons are structured within an atom. Why do these matter? Why does it matter how these electrons move? Well, it has to do with um, the physical attributes of the material that these atoms create. Um, it turns out that these movements um, uh, describe the behavior of a material in a lot of interesting and useful ways. And that one way we come to understand that is by what's called the Pauli exclusion principle. The Pauli exclusion principle isn't something that's particularly intuitive, but I think you're probably familiar with it from chemistry. But what it says is that no two electrons can have the same set of quantum numbers. In other words, we have those four quantum numbers, n, ml, ms, and l. And if I have one electron around an atom that has an n of, whatever, 2 and an L of 1 and a ML of 0 and an MS of a half, I can't have another electron that has those same values. Something needs to be different. So if we look at a really simple 3-electron model here, this is a possible state, right? Because you have an N of 1 here and a MS of half and negative half. And then you have at N2 a electron with a ms or a spin of plus 1/2. So that works okay. But if we tried to get all three of those electrons into the energy level 1, it wouldn't work because in this state we would have two electrons here that have an n of 1 and both have an ms of a half, and that's not allowed. This isn't allowed either, again, because we can't have two electrons with the same set of values. And when you get into more complex electrons, the same holds true. You can't have two electrons with the same set of four quantum numbers. Let's see what that looks like when we start building atoms with electrons. As we saw before, as the energy level n grows, the number of available ML and L options grow, right? So we looked at this before. What this means is that, for instance, if my n is 4, then I have 4 possible L's, right? It can be 0, 1, 2, or 3. If my n is 1, then the only L that is possible is 0. So let's look at, for instance, what can fit inside each energy level. In energy level 1, I only have one possible L, that's 0, but we give them letter names. And then I can have an up or down spin. Okay. In n equals 2, let's see, over here I see that then I can have L's of 0 or 1. That's my S or P. In the S level, where my L is 0, then I can only have an ML that is also 0, and I can have 2 spins within that, so I can fit 2 in there. At the N level of 2 with an L of 1, okay, then I can have an ML that is 0, -1, or 1. And each of those can have an up-down spin. So that gives me 6 that fit in that level. And so on. As we go on to the next one, we'd find that the next value there is 10. And so this is just a list of electrons that you have at the N2 level, right? At N2, our possible L's, as we see over here, are 0 and 1, right? So we have 0 and 1. At the L level 0, I can only have an ML of 0, right? And I get a plus or a minus spin. Um, at the L level of 1, I have 3 possible MLs. Each of those has this up-down spin, and that's where I get that 6 that you see down here. All right, so a larger number of electrons exist at the higher energy levels, as we just sort of figured out there. What does that mean when we start looking at actual elements? Um, First of all, when we talk about these elements, we're talking about a stable atom. That is when each of the electrons um, are at the lowest possible energy level. Um, but let's look at aluminum. Aluminum has an atomic number of 13. So at a stable state, it's got 13 electrons. The first 2 go in the 1s shell. Okay. The next 2 go in the 2s shell, which is these here. The next 6 go in the 2p shell, which is here. So that gives us 10. The next 2 go in the ms or the 3s shell. And then finally, we have 1 electron in the 3p shell. And that's how we end up here. And so if we added 1 electron and proton to that, we'd have silicon and so forth. In this case, we only have 1 in that p shell, which gives this aluminum a particular set of behaviors, right? And so the colors here you can see are similarly behaving elements. So we see there are similar behaving elements here in this direction because they have a similar emptiness in their p shell. The noble gases here behave very similarly because they have a full p shell and nothing in the next level. There is some uncertainty here, right? Because if you look at this, you can see that 3p fills and then you get 1 more electron, so you get a 19. So we would think it would go into 3d, but instead it goes into 4s. And that's just because this is actually more tightly bound, that 4s, than the 3d is. So there's, as you get more higher in the table, things get a little more complicated. Here's just a list of some of those characteristic behaviors of these particular elements. And again, you can see that they have to do with oftentimes how much is left in the last shell, right? So if I have 1 in my S shell, I get all of these alkali metals. If I fill my S shell, I get all these alkaline earths, and those have similar chemical characteristics. All right, so one last thing to talk about here, and that's just to make sure that we understand that the periodic table gives us the ground state of atoms, the lowest energy version of the atom. But if we add energy by, say, adding photons, it'll increase the energy level of the electrons. So sodium in its ground state looks like this. But if we add energy, we might bump one of those electrons up from this 3s to a 3p level. That means in this state, this is unstable. It's unstable in sort of the way that a ball at the top of the hill might be unstable, right? If we have a ball sitting at the top of a hill and we push it a little bit, it's going to go back to its ground state where the ball is resting at the bottom of the hill. This is the same sort of idea here. There's a certain amount of energy required to get your electron to this level. And if something, changes in that atom, it can result in the ejection of a photon, which would bring it back to its ground state, to its more stable state. So these energized electron or atoms don't tend to last very long. They tend to be stable or unstable rather. But if we add enough, we can actually remove that electron from the atom. So in the case of sodium, that would mean we'd have 11 protons, but only 10 electrons. And that's what we call an ion, of course. And one last point, just roughly speaking, the more loosely bound the outermost electrons are, the more unstable the element is, and the more likely it is to join with compounds. So something like the noble gases, which have filled their that three that p level, um, tend to be very stable. They don't join with other elements very well. They don't change very much. But other elements that don't fill their shells tend to be more unstable. All right, that is atomic physics, or as far as it into atomic physics as we're going to get.